And let me introduce Steve Glaser. He's a principal architect and also member of the PCI SIG board. Steve?
Sure, thanks. So I'm going to talk a little bit about some of the use cases, particularly use cases that we at NVIDIA are interested in. Come on. Oh, works better if you hit the right button. Okay, so what's going on? We've got, actually, increase the deck. Come on. Oh, there we go. That works better. So I want to talk a little bit about cache coherence. What does it do for accelerators? Talk about it using it as expansion memory for CPUs, looking at some flexible configurations, and then talk a little bit about security. Come on. There we go. So from an NVIDIA product standpoint, we're moving from the, well, not moving, we're supporting both the left, but we're also moving towards the right model. Today we have a Grace CPU and a Hopper GPU. Those are our high performance on-chip. Okay, so that's the high performance on-chip interconnect or chip-to-chip interconnect. It uses a version of NVLink, and we're going to be moving to also supporting a CXL coherent link using an industry standard CPU and NVIDIA GPU. So what do we need to make this work? Well, first of all, why do you want it? We want shared virtual memory. We want a single address space for everything so that the GPU and the CPU see the same virtual address space, they see all the same APIs, they see all the, a single malloc. It basically makes the world doable. You can take an application that's running on a CPU and move pieces of it to the GPU and not have to move, or not have to architect everything all up front. So you get the same, everything's the same. Atomics still work, shared memory still works. It's just the same program running in two places. How do you get there? Well, CXL is a good way. So what do you need it for? What do you want for CPUs? Well, one of the problems you've got with CPUs is the DDR channel is constrained. You've got a physical bus that's very short, it's running really fast, and you have applications that want more memory. So if you put a CXL memory device attached to a host, particularly with the caching, you can hide some of the latency of that CXL memory so that the performance degradation of being on a slower bus isn't as big a deal. It gives you a flexibility for memory, for the choice of what you can put out there. You can use DRAM, you can use storage class memory, all sorts of stuff. Another big application that we're interested in is pooling. In a data center, you have to build for the worst case right now. So that means every host has to have enough memory to support the worst case application you want to run on it. With memory pooling, you can have a pool of memory, lower performance of course because it's on a switch, but you can assign that pool dynamically to the host that needs it, and you don't have to populate all that memory on every host. So it gives you a disaggregated memory kind of configuration. We think that's going to be key in allowing particularly the cloud kind of applications to work where you've got a variety of things that need to be configured over time, and it changes over time. Come on. It's better if it's not behind me. Come on. Another key advantage, or another key use case for us is GPU expansion. So today we have a host connected to a GPU, and we have high bandwidth memory in-package memory. HBM is clearly limited in capacity. We want really high bandwidth, so that gives us, or HBM gives us that high bandwidth, but we also want more memory. Today we're using host memory. That means that that single bottleneck or that single interconnect between the host is becoming a performance bottleneck. By putting CXL memory, you can put as many channels as you want below the GPU and get the whatever bandwidth you want. And GPUs are good at caching, so they, again, the GPU's caching structure can hide the latency. So this gives us a tiered memories approach. We can also you can mix and match, so you don't have to populate the CXL memory at all at day 0. You could add it as an add-in card of some kind. Similarly, if you have a switch below the GPUs, you can create a pool at the GPU level. So you're, instead of pooling at the host level, you can do the same thing at another level. So you've got a CXL memory pool that's shared across all 3 GPUs, and that can be either static pooling, or we could do the sharing stuff that CMAC was talking about. And you can pick and choose which one you want. Similarly, you can do a mix and match with the switch between the host and the GPUs. And this is kind of the same picture that CMAC was talking about, but adding the GPUs to the picture. So we now have a CXL memory pool. It's shared across the hosts. It's also shared across the GPUs. And you can also have DMA devices, NICs and things similar, that can DMA either into host memory, GPU memory, or CXL pool memory, and they don't particularly care which one they're doing it into. They just write to memory, and it's just an address. And that this could also be a switch that's, it could be a straight CXL switch, or it could be using some other memory or some other interconnect. It doesn't have to be the PCI/CXL interconnect underneath. One of the key requirements for this that really is important is the back and validate feature that's part of CXL 3.0. Because what that lets you do is have a memory device that, if you come in with a DMA transaction, say from a NIC or another GPU, you're doing a read into what is actually in CXL memory, that CXL memory can send it back and validate to whoever owns the cache line saying, I need it back. And that really enables the peer-to-peer stuff to work. Without it, you have to go, everything has to go through the host, and the host is, becomes a performance bottleneck. Wow, I went through this really fast. So, and lastly, one of the things that is evolving in the industry is confidential computing. This is the ability to have a shared nothing kind of environment where you don't, or actually it's trust nothing. The vendor, say Amazon or Google or somebody that's making a cloud service, could offer a trusted virtual machine that's running partly in the host, partly in the GPU, and partly in the CXL memory. And you don't have to trust any other TVM. You don't have to trust the hypervisor or the firmware. You may not even have to trust the switch. We think that's a key advantage and a key requirement for moving forward, because you're going to have large deployments and you need to be able to keep them secure, provide the isolation between the various virtual machines. And we think that CXL and building on top of the PCI SIG Gen 6 stuff is a really good combination. One thing I'd like to point out also is that the flit mode stuff that's part of CXL 3.0 is enabled by the flit mode stuff in PCI 6.0, but it's not required. You don't have to go to the 64 gig speed grade to get the CXL 3.0. You could do CXL 3.0 at any speed. Similarly, you can do PCI Express flit mode at any speed. And I think given that some vendors' PHY implementations may be a little longer in time than we would like, there may be an interesting application for CXL 3.0 running at 32 gig. And wow, I'm ahead of time. So I guess, let's see, so questions? Sure.
Please use the microphone because we're recording.
back to the slide there.
Come on.
I have two questions. One is on the component attestation and authentication, and the second is on the link encryption. Do you see both of them as responsibility of the VM, or it's more of a platform responsibility, providing link encryption and device attestation, and then the VMs derive that trust from the platform?
It's a good question. The security model is an evolving model. In the ideal world, you trust nothing, so that the VM would do all of the authentication work so that it knows what it can trust. It's going to be a while before that can happen, and so there's going to be a mixture. Link encryption is based on the CXL link encryption is based on the PCI Express link encryption, or what's called IDE, and it is a point-to-point port level trust. So if I encrypt a link that says everything that's on this link is encrypted to the next hop, and then it gets decrypted and then re-encrypted on, if that's a switch, it gets re-encrypted on the other side. So that kind of requires you trust the switch, which is not necessarily what the VM people would like. They would like to trust less things. But trying to do what PCI calls a selective IDE is problematic for CXL. It would create a lot of latency issues that we don't really want to deal with at this stage.
So when I ask this, I want to make sure I'm speaking industry, not NVIDIA, because I don't want to give away anything away from your company.
Okay.
Do you believe that the first compute devices, or be it the actual video cards, will be CXL Type 2 or Type 3, in your opinion? And do you believe that the first CXL Type 2 devices, or CXL compute modules or GPUs, will be Type 2 or Type 3?
GPUs will be Type 2. We will want Type 3 memories, but what some people are calling Type 3 plus, which is Type 3 with back and validate. Type 3 with back and validate is what enables this kind of picture.
So do you believe that you'll first hit the consumer market? Sorry, not you, but again, the industry will first hit the consumer market with actual video cards doing kind of stuff, or it'll be more compute modules for the server market?
Compute models for the servers, what I believe.
Okay.
But,
So I would like to know more about, when you say ease of programming model, how do you envision your NVIDIA's CUDA libraries to evolve with the support for CXL, or basically a shared expansion memory as you're showing here?
we already support CUDA with a fairly transparent API across the platform. We're doing it today with the Grace Hopper kind of world. We've been doing it for quite a while, so it's not really going to change, but it's going to. But having a single address space is what really is the fundamental that enables the evolution. You don't have to change your entire program at once. You can move pieces of it over to the GPU.